Okay, so let's get started. So one of the first gas laws we're going to be talking about is going to be Boyle's law. And Boyle's law, remember, relates pressure and volume. And it turns out that pressure times volume is equal to a constant. In other words, they are P and V are what we call inversely proportional. Okay, so the equation that we use will be P1, my initial pressure and initial volume, is equal to P2 times V2, my final pressure and my final volume. So in this case, we have V1 the pressure. This is P1 and this is P2. So we're looking for V2. So we'll just put our numbers in our formula. Okay, so we have all of our values here. We have our formula. We rewrite our formula by dividing both sides by P2, then plug in our numbers. And notice we didn't need to convert our pressure to atmospheres because as long as their units are exactly the same, they'll cancel out. And our answer will be given in liters and two significant figures. Okay, what about a sample of neon gas? Okay, it occupies 250 milliliters at 880 torr. So this is V1, this is P1. And we're going to calculate the pressure of neon, P2, if the volume is increased to 1 liter. This is V2. Now here's the note, convert milliliters to liters. Remember, we have to have the same units. So before we start, we'll say V1 is equal to 250 milliliters. And we divide by 1,000 milliliters, 1 liter, and we get 0.250 liters. Now we're going to solve for P2. So I'm going to divide both sides by V2. And now we can start putting in our numbers. P1 is 880 torr. V1, we just converted to liters, 0.250 liters. And V1 is 1 liter. V2 is 1 liter. Okay, so what we get is 2.2 times 10 to the 2 torr. Now why do I write it this way? Because this is two significant figures. So your answer should have two significant figures. We have nitrogen at 65 liters. It has a pressure of 745 millimeters of mercury. So this is P1. This is V1. And if we transfer it to a 25-liter bag at the same temperature, so we're holding that constant, then this is V2. So we want the pressure. So here, they're both in liters. My pressure is in millimeters of mercury. So P2 is equal to, I'm going to divide both sides by V2. Okay, so now we can just plug in our numbers. We have 745 millimeters mercury. V1 is 65 liters. V2 is 25 liters. Okay, so P2 is equal to 745 millimeters mercury times 65 liters divided by 25 liters. And I get 1,937 millimeters mercury. And each of these are in 3 significant figures. So you get 1.94 times 10 to the third millimeters mercury. So it's going to be 1,940. Okay. One more. If we're going to do another Boyle's Law problem, the volume of a gas that occupied 275 milliliters at a pressure of 825 millimeters mercury. So this is V1. This is P1. And we increase the pressure to P2, and we want V2. Okay, so notice though that P1 and P2 are different units. So first, we're going to convert P1. So P1 at 825 millimeters mercury, and look at your table conversions. We know that for every 1 atmosphere, it's 760 millimeters mercury. So 825 divided by 760 is equal to 1.08553 atmospheres. It's going to be 3 significant figures, so just make sure we note that. Okay, so now we're looking for V2, so we're going to divide both sides by P2. Remember our initial equation. Let me just write our initial equation down. The Boyle's Law, P1V1 is equal to P2V2. So if we're looking for V2, we're going to divide both sides by P2. And so P1, the 1.08553 atmospheres, times V1, which we said was 275 milliliters, divide that by P2, which is 1.50 atmospheres, and we get 199, and we want 3 significant figures. 199 milliliters. Okay, so that would be our new volume. Now, does it make sense? We've increased pressure, and we know volume will decrease when we increase pressure. So it makes sense that my volume's decreased. Okay, so let's take a look at temperature and gas law problems. So if we take a look at temperature, then what we find is that we need to use the Kelvin temperature, okay? And the reason is this: there is no negative energy. If temperature and average kinetic energy are related, then you can't have a negative kinetic energy. So what we do is we set for the Kelvin scale, we have an absolute zero. What that means is that the zero set at absolute zero means there's absolutely no energy whatsoever in that substance. No vibration, no motion, zero energy. So it's a hypothetical. We can get close, but it's a hypothetical absolute zero. Okay, so when we do gas law problems, always use Kelvin. Okay, and how you convert is you take your Celsius temperature and then you add 273. Okay, and some of you know that if you want greater precision, it'll be like 273.15. But what I want is for you to know this equation. Okay, so since we know that volume and temperature are related, so if I increase the temperature, the pressure is the same, then the volume has to expand. Okay, if I decrease the temperature, then the volume will decrease. So when we write that volume divided by temperature is equal to a constant, then what we get is this equation, and this is Charles' law. V1 over T1 is equal to V2 over T2. Okay, so let's do an example. So in this example, 3 liters of gas at minus 15 degrees Celsius, so this must be V1 and this must be T1, is allowed to warm up to 27 degrees Celsius. So this must be T2. And what is the gas volume? We're looking for V2. So what are the first things we need to do? Volume in liters, that's fine. But all my temperatures are in degrees Celsius, so we need to convert those. So T1 in Kelvin is going to be equal to minus 15 degrees in Celsius, right? Because remember the equation we just saw before was that the temperature in Kelvin is equal to the temperature in Celsius plus 273. So we're going to add 273 to this. And what we get is 258 Kelvin. Let's convert T2 now. So T2 in Kelvin is equal to 27 degrees in Celsius, right? Plus 273. And what we get should be 300. The decimal point here, just to remind us, is 3 significant figures. So now we can solve our problem. So we're looking for V2, so I'm going to multiply both sides by T2. So V2 is going to be equal to V1 over T1, multiply both sides by T2 times T2. Okay, so now I can plug in my numbers. V1, we said, was 3 liters. T2, we said, was 300 Kelvin. Divided by T1, which is 258 Kelvin. And our answer will be in 2 significant figures because this has 2 significant figures. So it's going to be 3 times 300 divided by 258. So we get 3.5 liters. So what we're saying is when I heat up my system, my volume increases. Okay, so let's do another example. All right, gas has a volume of 3 liters at 10 degrees Celsius. That's V1, that's T1. What is the temperature of the gas if it expands to 6 liters? So this is V2. And we're going to give the temperature, we're going to solve for Kelvin, and then we're going to convert that into Celsius. Okay, so let's rewrite our formula. We're looking for T2. Okay, so I'm going to multiply by T2. And then I'm going to multiply by T1, so V2 times T1 divided by V1. Okay, so let's get all our values. So first, T1 is going to be equal to, in Kelvin, is equal to my Celsius plus 273 say plus 1.5. Okay, so that'll be 283.15 Kelvin. Okay, T2 we don't know. We're going to find it and then convert. we have V1 and V2. So let's plug things in. So V2 is 6 liters. T1 is 283.15 Kelvin. V1 is 3 liters. Our answer will be in 3 significant figures. Okay, so T2 is equal to 566 degrees Kelvin. Okay, so we didn't specify here, but typically we like to go back, if we can, to Celsius. So when we want this in Celsius, we take our Kelvin and we subtract the 273. Okay, and what we get is 293 degrees Celsius. Okay. All right. Okay, so let's do another Charles Law problem. At 321 Kelvin, the gas occupies 635 milliliters of volume. So let's call this T1 and this V1. If the temperature is decreased to 216 Kelvin, then this must be T2. What is the new gas volume? So we want V2, okay? And in this case, we don't even have to convert any of our temperatures to Kelvin. They're given in Kelvin. So if we write down Charles' law, and we're looking for V2, we'll multiply both sides by T2, and then we'll just go ahead and plug in our numbers. So V2 is going to be equal to T2, which is 216 Kelvin, times V1, which is 635 milliliters, divided by T1, which is 321 Kelvin. And our answer will be in 3 significant figures. So 216 times 635 divided by 321. We get something like 427 milliliters. Okay? So, does that make sense? If I decrease the temperature, my volume will shrink. Okay? All right, last problem, and then we'll move on. A gas occupies 525 milliliters at a temperature of 89 degrees Celsius. So this is V1, and this is T1. And what is the volume of the temperature if the gas is cooled to 8 degrees Celsius? So this is V2, and we are looking for V2. So we're going to have to convert our temperatures into Kelvin, which is, you add 273. Okay, so 273 plus 89, we get 362 Kelvin. And T2 we want in Kelvin equal to 8 plus 273. Add that together, we get 281 Kelvin. So now if we write our formula down here, V1 over T1 is equal to V2 over T2. We're looking for V2, so we're going to multiply both sides by T2. Okay, so now let's go ahead and plug in our numbers. So V2 is equal to T2, that's 281 Kelvin, times V1, which is 525 milliliters, divided by T1, which is 362 Kelvin. Notice how my units cancel out. Our answer will be in 3 significant figures. So 281 times 525 divided by 362, and we get 408 milliliters. Okay, let's move on to Avogadro's law. In Avogadro's law, basically, if we're keeping constant temperature and pressure, then the volume is proportional to the moles of gas. And if you ever blow up a tire or a balloon and you're blowing and huffing and puffing into your balloon, your volume will expand in the balloon because you're putting in more air. And that's all we're saying, that how much air you put in will determine the volume. So if I double the amount of air, you're going to double the volume. Okay, so if you have 4 molecules that take up this unit of volume, then you had 4 molecules of here, it'll take up that same volume if it's the same temperature, same pressure. Notice it didn't matter what type of gas. It's just I have 4 gas molecules. It's going to take up the same volume. Okay, here when you do the reaction, notice that because I'm forming twice as many, I have a total of 8 molecules, I have twice the volume. So it turns out, under constant temperature and pressure, if I have basically everything in the gas form, you can use your volume to do your stoichiometry. Okay, so if we're following this, if my temperature and pressure are constant, they have 12 liters of hydrogen gas. We want to know what volume of nitrogen gas. So all we have to do is use the stoichiometry to determine that. In other words, 12 liters of hydrogen, and we know that for every 3 hydrogens, I get 1 nitrogen. And I'm basing it off the stoichiometry on my balanced equation. The hydrogens cancel out, so this is my mole to mole, because we're changing substances. And that tells us I only need 4, this is 3 significant figures, liters of nitrogen. So 12 liters of hydrogen react completely with 4 liters of nitrogen. And so we're using our mole to mole ratio, but just so you know, with the stoichiometry, but just so you know, because of Avogadro's law, we can work with volume. Okay, now what about units? Well, remember, mole to mole ratio, this is unitless. We always write the units in so we can cancel everything out when we do the transfer. Just so you know, mole to mole ratio, the ratio of this based on the coefficients, that stoichiometry is going to be unitless. Okay, so let's try another one. Constant temperature and pressure. What volume of oxygen, how many liters are required to make 45.6 liters of water or water vapor? So we're starting out with my water vapor. And all we're doing, the volume's the same. All we want to do is change substances. So if you change your substance, then we need a mole to mole ratio. So let's do our mole to mole. So for every 2 water vapors that are formed in this gas state, I need 1 oxygen. I'm changing substances only, so again, it's going to be now liters of oxygen. And so it's going to be half of that, so it's going to be 22.8 liters. Okay, based on my stoichiometry. Okay, and that's what Avogadro's law just tells us. If I have a gas that occupies a volume V1, then if I double the gas, it'll be twice that volume. If I have half the amount of gas, then it's going to be half that volume. Okay, so let's talk about the combined gas law. And the combined gas law is a combination of Charles' law and of Boyle's law. So you can see here what I've circled in red. P1V1 is equal to P2V2. That's Boyle's law. And if we look at what I have in green, the V1 over T1 is equal to V2 over T2. That's Charles' law. So the combined gas law, like I say, is a combination of these two. And what we're doing is all we're holding constant now is the number of moles of gas particles that we're using. So when you see any problem that changes both pressure, temperature, and volume, then we're looking at the using the combined gas law. Okay, so also what it tells you here is that if we talk about the volume of a gas, you need temperature and pressure. That's the triumvirate. Those three have to go together. Okay, so it's really important that you know whenever we talk about the volume of a gas, you need to know the temperature and pressure that goes with it. Okay, the definition now, whenever we talk about this, we have to set a standard so everyone knows how to compare apples to apples. And so when we talk about STP, this is standard temperature and pressure, it's 0 degrees Celsius to 73 K and 1 atmosphere. That is the definition, okay, for STP. Anytime you see us use this abbreviation, you're thinking, oh, 273 Kelvin, 760 torr. All right, so here, a sample gas occupies 125 milliliters at STP. So here's my volume. In standard temperature, so we have T1, and pressure, that's P1. What is the volume of the gas at 65 degrees Celsius? That's T2. And 320 torr, that's P2. And the volume is what we're looking at. So we're going to use our combined gas law, and I'm going to multiply both sides by T2 and divide both sides by P2. So you get V2 by itself, and P1 V1 over T1 times T2 over P2. Okay, so before we put in our numbers and do the calculation, so we have STP, and we know that 1 atmosphere, that's the definition, is 760 millimeters mercury, or 760 torr. So that's our conversion. Okay, so now we know what P1 is. And the reason we're doing this is because, remember, this is in torr, so we want the same units. Temperature, we know T1 is defined to be 273 Kelvin. Okay, and if you want 273.15 Kelvin. T2, we're going to add, remember in Kelvin, we want to take our degrees in Celsius and add 273. Okay, so what we get is 338 Kelvin. Okay, so we have T1, P1, T2, P2, and V1. So now we can substitute everything in, and our volume will now be in milliliters. So P1, we said, was 760 torr. V1 is 125 milliliters. T2 is 338 Kelvin. And we're going to divide this by T1, the 273.15 Kelvin. And we're also going to divide by P2, which is right here, 320 torr. And our answer is going to be in 3 significant figures. So 760 times 125 times 338 divided by 273.15 and divided by 320. So we get 367. And what are my units? Torr cancels out. Kelvin cancels out. So my units are going to be milliliters. And that's going to be our new volume. Okay, so let's do another example. So in this example, we want the volume, we'll say that's V2, at STP. So this is going to give us T2 and P2. And this is that occupies, so this is what it originally had, 1.62 liters at P1, 616 torr, and this is T1, 42 degrees Celsius. So we're going to use V2, going to multiply both sides by T2, divide both sides by P2, get P1 V1 over T1 times T2 over P2. Okay, so let's take a look at our units. V2, V1 is liters, V2 we can have in liters, that's good. What about P1 is in torr? And we know, as we discussed previously, that 1 atmosphere is the same as 760 torr. That's our conversion factor. So we know that we don't need to go beyond that. So now everything's going to be in torr. And in T2, standard temperature and pressure, the temperature is 273.15 Kelvin. But T1, we need to convert. And we know it's going to be 42 degrees Celsius plus my 273. So in Kelvin, that gives us 315 degrees Kelvin. So now that we have our units, we can go ahead and fill everything in. P1, 616 torr times V1, which is 1.62 liters, times T2, which is our 273.15 Kelvin. All of this is divided by T1, which is 315 Kelvin, and P2, which is 1 atmosphere, or also 760 torr. So our answer is going to be in 3 significant figures. That's by definition, right? So if we do that, 616 times 1.62 times 273.15 divided by 315 and divided by 760. Okay, so I get a 1.14, and let's take a look at our units. The torrs cancel out, kelvins cancel out, so I get my units in liters, which is good, and it's 3 significant figures. Okay, all right, combined gas law problems. Here, now how do we know it's combined gas law? Because I'm changing temperature, and I'm changing pressure, and I'm looking at volume. So I need all 3. Okay, so the balloon is filled with 266 liters at this temperature. So V1 is equal to 266 liters. T1 is 38 degrees Celsius. So we have to add our 273 to it. And so in Kelvin, we get 311. And P1 is equal to 0.995 atmospheres. Okay, so V2 is what we're looking for. T2 is going to be equal to the minus 76 degrees plus 273. So that's going to be equal to 197 degrees Kelvin, and P2 is equal to 0.561 atmospheres. So now that we've done all our conversions, let's go ahead and do our calculation. So we're going to use the equation P1 V1 over T1 is equal to P2 V2 over T2. That's our combined gas law. We're looking for V2, so V2 is equal to P1 V1 over T1 times T2 over P2. So let's go ahead and put our numbers in. So V2 is equal to 0.995 atmospheres times V1, which is 266 liters, divided by T1, which is 311 Kelvin, times T2, which is 197 degrees Kelvin, divided by P2 is 0.561 atmospheres. Okay, our atmospheres cancel out, our Kelvin cancels out, so our units are going to be in liters. So that part's good. Everything's three significant figures, so 0.995 times 266 times 197 divided by 311 and divided by 0.561. And we get 299 liters of gas for our volume. Okay, so what happens if we have a single equation relating all the properties? So here, when we look at the ideal gas law, it's PV equals nRT, and this is really something you should remember. PV equals NERT, PV equals nRT, but we should know what this is. So if I held my temperature and the moles of gas constant, then you're going to see the aspect of Boyle's law here. If I held my pressure and the moles of gas constant, then I have Charles' law. If I hold my pressure and temperature constant, so the volume is related to the moles of gas, I have Avogadro's law. And R is called the universal or the ideal gas constant. And it's the typical value that we use for it is 0.08206 liter atmospheres per mole degrees Kelvin. Okay. Okay, so let's take a look at this ideal gas constant. Let's try to determine R at STP. So we have a volume equal to 22.4 liters for 1 mole of gas. What would R be equal to? So at STP, we know it's going to be 1 atmosphere. The volume is 22.4 liters. The temperature, defined by STP, is going to be 273 Kelvin, and the number of moles of gas is 1. So if we just go ahead and rearrange our equation to solve for R and plug in our values, we see that R is equal to 0.0821 liter atmospheres per mole Kelvin. Okay, so make sure we keep an eye on our units. That's really important. So let's do another problem, and we want to know how many moles of helium are contained. So we want N are contained in a volume of 0.900 liters at a temperature of 30 degrees Celsius and a pressure of 0.8 atmospheres. And we'll use R with the value 0.08206 liter atmospheres per mole Kelvin. Okay, now what's interesting about this problem, when comparing it to the Boyle's law, Charles' law, and the combined gas law, here I'm not changing any conditions. All I'm asking is I want one variable value and I'm given the rest, but we're not saying I've changed anything. So that's a way you can read the problem and determine what equation to use. So if we're looking for N, when I rearrange it, N is going to be equal to PV over RT. And we're going to change our temperature. Instead of 30 degrees Celsius, we're going to add the 273 to that. And we're going to get 303 degrees Kelvin. Okay. Now we can plug our values in. The pressure was 0.800 atmospheres. And whenever we use the ideal gas law, remember we have to keep an eye on our units. Pressure, since this is in atmospheres, must be in atmosphere. Volume must be in liters. Okay, so it's really important that we have the appropriate units. The volume here is, as mentioned, in liters. R 0.08206 liter atmospheres per mole Kelvin. And our temperature is now 303 degrees Kelvin. Okay, so if we look at our units, the liters divide out, the atmospheres divide out, and this is Kelvin times 1 over Kelvin, so that divides out. And remember, 1 over a fraction is equal to the value of my denominator. So in this case, the units of mole, 1 over mole, is going to be equal to mole. Okay, and that's the analogy. If I say 1 over 1/2, that's going to be equal to 2. Okay, so we treat our units and we treat our numbers. So now let's go ahead and work with the numbers. 0.8 times 0.9 divided by 0.08206 divided by 303, and we get it's 0.02896 moles. Okay, put the mole closer, and then 3 significant figures, 3, 3, 4. So we're going to have 3 significant figures here. So 0.029, that's 2 significant zeros, 0. This is 3 significant figures, moles of gas, of helium. Okay? So that's how you use the ideal gas law. And again, when you read the problem, if you're given your variables, but there's been no change to my system, consider using the ideal gas law. All right, let's take a look at this one. Ideal gas law. So volume, moles of gas, pressure, and temperature. No changes, so that's why we're going to use our ideal gas law. So we're looking for volume, so let me just rewrite my equation, okay, because it says what volume. So that's going to be equal to nRT over P. Now let's take a look at our variable. So N is equal to 0.393 moles of gas of nitrogen. Okay, R we know, that's a constant. 0.08206 liter atmospheres per mole Kelvin. Please make sure you have that access to that conversion. Okay, don't memorize it. Temperature was 24 degrees Celsius, but we want to add our 273 to that to get it into Kelvin because we're working with gases. So I get 297 Kelvin. Okay, so we have T. Atmospheres, we need P. P is 0.971 atmospheres. So now that we have all of our values in the appropriate units, we can now solve for our volume. So we have 0.393 moles times by 0.08206 liter atmospheres per mole Kelvin. Okay, running out of space here. So our temperature was 297 Kelvin. And our pressure, which goes underneath, was 0.971 atmospheres. Okay, so atmosphere divided by atmosphere, that divides out. Kelvin divided by Kelvin, that divides out. Moles divided by moles. So the remaining unit is going to be liters, which is good because that's the unit for volume. So let's do the calculation. 0.393 times 0.08206 times 297 divided by 0.971, and we get 9.86 liters. 3 significant figures, so this should be 3 significant figures. Okay, let's do one more. So we want the volume occupied by N equals 1.5 moles of gas at STP, so we know the temperature is going to be 273.15 Kelvin. Our pressure is exactly 1 atmosphere exactly. Okay, and R is equal to 0.08206 liter atmospheres per mole Kelvin. Okay, and we're looking for a volume. So let's rearrange our equation. V equals nRT over P and start putting in our values. 1.5 moles, 0.08206 liter atmospheres per mole Kelvin, and our temperature is 273.15 Kelvin. All of this is going to be divided by exactly 1 atmosphere. Our units, the moles cancel out, our atmospheres cancel out, and our Kelvin cancels out. So our volume is going to be in liters. So that's good because that's what we want. So 1.5 times 0.08206 times 273.15 divided by 1 gives me 33.6 liters. That's 2 significant figures. So it's 34 liters. Okay, so that's how you can do this. This is practice with the molar volume. Now, here's the thing. If we know at STP, let me just give you a different color. what is molar volume? So molar volume at STP. This is the volume of gas of exactly 1 mole of gas. Okay, so you could also use this as a conversion factor. Okay, so let me go ahead and show you how you would use molar volume at STP as a conversion factor. And I will do that in the light blue. Okay, so because we know we're at STP, what we can do is use the molar volume at STP as a conversion factor. If you're not at STP, you must go through the ideal gas law. However, if you are at STP, as you are in this situation, I know that 1.5 moles of gas, and for every 1 mole of gas at STP, it occupies a volume of 22.4 liters. So what we would get is 33.6 liters, and since this is two significant figures, we would get 34 liters. So in either case, either just directly using the ideal gas law or using the molar volume at STP, you will get the same answer. If ever in doubt, just go through the ideal gas law, because that is actually how we can calculate our molar volume. Okay, so you can use molar volume at STP as a conversion factor, or you can just use your ideal gas law for this problem. Okay, in this case, we have all these different variables. We're not at STP. So what we're going to do is just use your ideal gas law. Again, we're looking for volume, so V is equal to nRT over P. Let's get everything into our units. Okay, so not STP, use ideal gas law. So let's take a look at our units. Okay, so, oh, sorry. I'm sorry. All right, so N is equal to 0.55 moles. Okay, R is equal to 0.08206 liter atmospheres per mole Kelvin. T is 18.2 degrees Celsius plus my 273.15 to convert it to Kelvin. So we end up with 291.35, and if we remember, we're going to go to the least precise value, so we're going to stop at the 3. And then P is in millimeters mercury, so we have to convert that to atmospheres. And we use our conversion factor that 1 atmosphere is equal to 760 millimeters mercury. So 787 divided by 760, and we get 1.03553 atmospheres. Again, this is 3 significant figures, but we're not quite done with our calculations, so I'm not going to round it, okay, until we finish our calculations. So if we go back to our, now that we have all our values, we can go back to our equation and put in our values. 0.55 moles, 0.08206 liter atmospheres per mole Kelvin. Okay, and the temperature is 291.35 Kelvin. Okay, all of this is divided by our 1.03553 atmospheres. Okay, this stops at the 3, this stops at this 3. So, but we only have 2 significant figures here. So our answer when we're done will be in 2 significant figures. So it's 0.55 times 0.08206 times our 291.35 Kelvin divided by the 1.03553, and our volume is 12.7 liters, but we want 2 significant figures, so our volume is 13 liters. Okay, if we go back, just double check, our moles had canceled out, our degrees Kelvin cancel out, our atmospheres cancel out. So 13 liters is how much this gas will occupy. Okay. So what about molar mass of a gas? All right. So if we look at molar mass of a gas, then we know the molar mass, remember molar mass, I'm going to use a capital M for molar mass, is equal to the moles of your gas, your mass of your gas, excuse me. The mass of the gas in grams divided by the moles of your gas. And that's going to be moles, right? So remember, if I say, what's the molar mass of helium? And you look at it and you say, oh, isn't that 4.008? The molar mass has units of grams per mole. So molar mass is mass divided by moles. If I rearrange it, and moles, remember, is the variable is n. If I wanted moles, the moles would be equal to the mass of your sample divided by the molar mass. Okay, so just so you know where that comes from. Now, if that's the case, then what we do is we take this G, my grams, my mass, divided by the molar mass, and I put it in where N is. Okay, and that's how we get this formula. Okay, so we can use this. We use this form to determine the molar mass of an unknown gas. Okay, so here I want the molar mass. So let me rearrange this equation. Okay, and when I rearrange the equation, I'm going to multiply both sides by my capital M and divide both sides by PV. So the molar mass of a gas is going to be equal to the mass of my sample times RT over PV. All right, so let's go ahead and get our variables. So the mass, you see, is 0.210 grams. Okay, that's good. The pressure needs to be in atmospheres. So my pressure, which is 432 torr, when we convert, we know that 1 atmosphere is 760 torr. So our pressure is 432 divided by 760, and I get something like 0.56842 atmospheres. And this is 3 significant figures. Okay. Our volume, we want to convert that to liters. So 333 milliliters. Our conversion is 1 liter is 1,000 milliliters is 0.333 liters. Okay. And finally, her temperature is 23 degrees Celsius, so we're going to add 273 to that, and we get 296. Okay, Kelvin for our temperature. All right, so now we have G, T, PV, and we can look up R. So what I'm going to do, because of space considerations, I'm just going to write our values up here. So G is right here. R, 0.08206 liter atmospheres per mole Kelvin. And that's why we have to do all our conversions, because it's liters, atmospheres, Kelvin, and moles. So we have this. So we converted this. So P now is equal to 0.56842 atmospheres. Okay. I'm just rewriting it to give me space to do the calculation. All right. T we need to record, and V we can record. Okay. So let's go ahead and give me some space here. So we know T is equal to 296 Kelvin. V is equal to 0.333 liters. And again, this is G right here. All right, so let's go ahead and plug in all our values into our equation. So if we do this, then what we get, the molar mass is equal to 0.210 grams, okay, R 0.08206 liter atmospheres per mole Kelvin, and T is 296 Kelvin. All of this is divided by our volume, which is 0.333 liters, and our pressure, which is 0.56842 atmospheres. Okay, and if we calculate it out, let's take a look at our units, because we're talking about how important our units are. I don't have any other grams, so the grams stay here. The liters cancel out. My atmospheres cancel out. My Kelvin cancels out. So my units will be in grams per mole. So that's good. And we'll multiply it out, but notice I have 3 significant figures. Okay? So 0.210 times the 0.08206 times the 296 divided by 0.333 for my volume for the liters, and 0.56842 for my pressure. So for 3 significant figures, okay, it's 26.9 grams per mole. Okay, so whenever we want basically the molar mass of a gas, you're going to use this version, okay, of your ideal gas law. Or you can do 2 steps, get the moles and then divide your sample by the number of moles. But it's very easy to use this version of the equation. Okay, so, all right. Now, we know about our molar volume. We can use it as a conversion factor. So in this example, show that the molar mass of oxygen is 32 grams per mole. Okay, so here, 1 liter of oxygen at STP has a mass of 1.429 grams. Okay, so what we can do then is 1.0 liters of oxygen at STP, how many moles is that? Well, the number of moles that is, we know is 22.4 liters for every 1 mole. Okay, so basically we know that this is 0.04464 moles of oxygen. Okay, and yes, we're at 2 significant figures, but we're not done with our calculations yet. Since we know that molar mass is equal to the moles, is equal to the mass divided by moles, then we know that the molar mass, the mass was 1.429 grams, okay, divided by 0.04464 moles, because we just determined that. And what we get is 1.429 divided by the 0.04464, okay, we get 32, and this is going to be 2 significant figures. Get 32 grams per mole. And isn't that what we were saying? This is how we show that the molar mass of oxygen is 32 grams per mole. Okay, so let's take a look at this example. Okay, in this example, we want to get the molar mass. So again, what we can do is we can use a formula or do it in 2 steps. So let's see if we remember the formula. So the formula was PV is equal to the mass of your sample times RT divided by the molar mass. And we want the molar mass. Okay, so we could use this formula, or we could do what we did in the previous problem, and we use our molar volume. Okay, so let's do molar volume first, and then we'll do the formula. Okay, so we'll do the molar volume approach first. That'll be in black. So the molar volume, if I have 3 liters of gas, then I know for 1 mole of gas, and this has to be a STP, is 22.4 liters. So we know that this is going to be 0.13393 moles of my gas. Since we know that the molar mass is going to be equal to the mass divided by the moles, the mass of the sample was 5.35 grams. The moles, 0.13393 moles. Okay, and that should be up to 3 significant figures. And when I divide the two, 5.35 divided by the 0.13393, I get 39.9 grams per mole. Okay, so that's doing the approach like we did on the previous slide, using our molar volume to calculate it out. Okay, now let's take a look in red what happens if I use our formula. Okay, so if we use the formula in red, we're looking for M, so I'm going to rewrite the formula. M is GRT over PV. So my molar mass, we know G, we said was a 5.35 gram sample. R, we said was 0.08206 liter atmospheres per mole Kelvin. T was 273. 0.15 Kelvin, because that's part of the STP. P was exactly 1 atmosphere. And V, we said, was 3 liters. Okay, so if we do that, let's cancel out my units. Atmospheres cancel out. Liters cancel out. Kelvin cancels out. So my units will be in grams per mole, so that's good. Okay, so 5.35 times my 0.08206 times the 273.15 divided by 1 and divided by 3, and I get, again, 39, in this case, 97 grams per mole. So, now why the difference? It has to do with the rounding errors that we introduce when we only use 3 significant figures for our molar volume. So, essentially, you get your 39.9. So either approach will work. Okay, so let's do one more practice. So here we want the molar mass of unknown gas, and we have 0.76 grams occupying a volume of 754 milliliters at 23 degrees Celsius and 342 torr. So here, since we're not an STP, we're going to use the ideal gas law. Okay, so when we look at the ideal gas law, what we're going to do is we're going to use a modified version. So remember, since we're looking at molar mass, that's equal to G over M times RT. Since we're looking for molar mass, so M is equal to G RT over PV. So let's go ahead and get all of our values, and then we can plug them in. Because we know R is going to be in 0.08206 liter atmospheres per mole Kelvin, we have to make sure that all our units match. So G is our 0.768 grams. R, we have T is equal to 23 degrees Celsius. So we're going to add 273 to this to convert it to Kelvin. So we get like a 296 Kelvin. Okay. P for pressure is going to be equal to 342 torr, but we need to convert that to atmospheres. So we know that 1 atmosphere is equal to 760 torr. So we get a pressure of 0.450 atmospheres. And finally, V is in milliliters. It's 754 milliliters, and we had to convert that to liters. So 1,000 milliliters is in 1 liter. So that's 0.754 liters. Okay, so now let's go ahead and start plugging in our values. What I'm going to do, I'm going to list our values to the side and then start plugging away. All right, so we know R, we know G, so T is 296 Kelvin, P is 0.450 atmospheres, and V is 0.754 liters. Okay, so using our equation, let's see what our molar mass is. So molar mass is equal to 0.768 grams times R, which is 0.08206 liter atmospheres per mole Kelvin, okay, times K, which is T, the 296 Kelvin. Divide this by the pressure, 0.450 atmospheres, and all that's divided by our volume, which is 0.754 liters. And if we look, our atmospheres cancel out, our liters cancel out, and our Kelvin cancels out. So the molar mass will have units of grams per mole. And let's see, 0.768 times 0.08206 times 296 divided by 0.45 divided by 0.754, and I get 54.979 grams per mole. We want 3 significant figures, so that's going to be equal to 55.0 grams per mole. So basically, that's going to be our molar mass. All right, so here's your penultimate breakout session, the breakout session just before the last one, and these are all using your gas laws. Let's continue. Let's talk a little bit about kinetic molecular theory. And what it is a general theory. It's going to explain the behavior of gases and by understanding the motions of gas particles. Now, there are a few assumptions or postulates we need to make. 1, gases are tiny. They have negligible volume. Okay, so the volume is negligible. Okay, it's mostly empty space between them, and they have no attraction for one another, so they'll just pass like ships in the night. Okay, and when they move, they have perfect collisions, and they move linearly, so you're not going to see an arc. It just goes directly from A to B. And when they collide, they're perfect collisions, so they don't smush or anything. There's a perfect transfer, if there has to be, of energy. Okay, so we don't lose anything there. Kinetic energy, okay, is the same for all particles regardless of their molar mass at the same temperature. Okay, this is the average. So if you look at an individual helium atom, it might be higher or lower. But if I say my temperature is 298 Kelvin, then all my helium particles will have the same average kinetic energy. Even if I compare helium in my gas mixture with oxygen, with nitrogen, they all have the same average kinetic energy. Okay, so it doesn't matter about the molar mass. But what that does mean is if it's like looking at a huge 18-wheeler truck and a little motorcycle, if they both have the same kinetic energy, if I have a lot of mass, then the velocity is slower than if I have a low mass, like a motorcycle, then it has a higher velocity. Okay, so this is directly proportional. So basically, if I increase my temperature, I increase my average kinetic energy. Okay, and gases that actually behave according to these assumptions are called ideal gases. Now, as you know, in reality, ideal gases don't exist because they're ideal. So we have real gases. So what's the difference? So basically, for most temperatures and pressures that we work with, they behave like ideal gases, and that's why we haven't differentiated really between the types of gases. However, when the pressures are high under small volumes, you're going to see more gases deviate, because if I'm trying to crush all my gases into a small volume, then now their sizes will have an effect on it. And at low temperatures, because they can't really bounce off each other, their attractions to each other, basically at lower temperatures, you'll see more intermolecular interactions. Okay, now let's talk about partial pressures. So let's go back to just assuming ideal gases, because we typically work in the ranges for our gases to behave like ideal gases. So if I have a mixture of gases, and most of the time when we talk about gases, they are mixtures, then the total pressure is the sum of each of the different types of gases. They're partial pressures, and it totals up to this total. Okay, so what does that mean? Like in air, we have mostly nitrogen and some oxygen, and then a little bit of other gases. So the total pressure is mostly from the nitrogen, but some comes from oxygen. And very little, but still, some will add up from all our other gases. Now, based on our ideal gas law and what we observe, they behave independently. So the nitrogen and oxygen in our air don't interact. Okay? How do we apply Dalton's law? So remember in experiment 3 and experiment 4 and experiment 5, where we're generating hydrogen and oxygen? Well, we collected it over water. So what happens is, not only is the oxygen, in this case the generator, okay, not only in this case the gas oxygen is collected over here, some of the water in here goes into the vapor state. So this is going to be a mixture of oxygen gas plus water vapor. Okay, so what's nice about when we collect our gases over water, we can determine what the vapor pressure is. This is temperature dependent. Okay, so why is that? Because it's a pure substance, right? All right, so the pressure of the bottle when we equalize it. So when we collected air, what you try to do is to equalize it. We know we try to get this level of my liquid in the bottle equal to the level in here. And when we do, that means that the pressure in the bottle is equal to the outside pressure that I can measure. If we look inside this bottle, the pressure is going to be equal to the sum of all the gases that are in there. In this case, it's going to be oxygen and water vapor. All right, so let's do an example. When we collected oxygen gas over water at 22 degrees Celsius and 662 torr, so that's my total pressure. How do I know this? Because when it says I collected oxygen gas over water, that means I have in that mix oxygen gas and water vapor. So if we know what the total pressure is in here at 22 degrees Celsius, then we know this is equal to the pressure of my oxygen and the pressure of my water vapor. So if we look it up and we see that the pressure, the vapor pressure of water at 22 degrees Celsius is 19.8 torr, then we can now determine what the partial pressure is of the oxygen. Okay, because that's what we're asking for right here. Okay, so the partial pressure of oxygen, remember it's the sum, so we add the 19.8 torr. This is from the water. So the partial pressure of oxygen is going to be the difference of the two. So 662 minus my 19.8. So we get something like 642 torr. Okay. You might hear us say, what is the pressure of dry oxygen. Okay. What this means is if I'm collecting over water, since I have a mixture of water vapor and oxygen, this is wet. So when we say dry oxygen, that means without the water. So this means without water. Okay, so just so you understand the terminology. Okay, so we'll just go through. Okay, in this case, for another partial pressure problem, so we collected 250 milliliters of oxygen that was collected over water. Okay, so this is my volume. Okay, at 23 degrees Celsius, so that's my temperature. And this is my total pressure. Okay, so you want to know what volume it would be from the oxygen. So our volume is going to change, right? So we're going to have to get, first of all, what the pressure is. Then we know pressure and temperature, we can get volume here. Okay, so the vapor pressure of water is 21.2 torr. So we know the volume's 250 milliliters. We know that the pressure is the sum because it's collected over water. That's key. It's the sum of the two. We know the pressure of water is 21.2 torr. So what we're going to do now is we're going to solve for the pressure of the oxygen using Dalton's law, and then we're going to solve for V using Boyle's law. So this is now doing multiple steps. Okay, so the pressure of the oxygen is, you're going to subtract the pressure of the water like we did in the previous slide. So this is the pressure of dry oxygen. Okay, now when we do this, we now know the pressure of the dry oxygen, and so we can use Boyle's law. All right, I just want to make sure this didn't change. So this again is V1. We wanted what's the volume, so we know it's V2 of the oxygen. Okay, same temperature. So here the vapor pressure of water is 21.2 torr. So we calculated from the previous slide what P1, okay, and P2 will be. So the vapor pressure of oxygen would be the 760, right, minus the 21.2. This is all in torr. So this is P1. Okay, and from our previous slide we said it was going to be the 738.8. Now we're going to, okay, so that's P1, but P2, now we're just looking at this when PO2 is 760. So we changed that to 760. Okay, so we have P1, P2, V1, and we want V2. Okay, so now we can just plug in our values. So this is from our previous slide, 739, because you're going to end there. 760 is P2, and the 0.250 is V1. So now we know what the volume would be if it were just purely oxygen at 700 with a pressure of 760 torr. Okay, let's continue. All right, gas density. Gases are really light. So whenever we talk about liquids or solids, we're talking about their density in grams per milliliter. But because gases are so light, our standard units are grams per liter. Okay, so the formula for density which you should know because we use it all the time. Density equals mass divided by volume, but in this case, whenever you're talking about a gas, you're going to be looking at grams per liter. Okay, so the density of a gas at STP can also be related to the compound's molar mass. Well, how is that possible? So here, this is molar mass, and that's grams per mole. And then at STP, we know that the molar volume is 1 mole per 22.4 liters. So the density would be grams per liter. So in other words, we can determine our density if you multiply the molar mass divided by, divided by our molar volume. And this is at STP. Okay? So, let's take a look at chlorine. So chlorine has a molar mass of 70.9 grams per mole. So at STP, we just divide it by the 22.4, and chlorine is fairly heavy. It's 3.17 grams per liter. Okay. So in terms of, it's not going to be per milliliter, so you want it in liters. Okay. So let's take a look at grams per liter of hydrogen and nitrogen. So in hydrogen, the molar mass of hydrogen is the 2 times 1.008 grams per mole. So that's 2.016 grams per mole. Okay, so the density is going to be equal to the 2.016 grams per mole. And remember, it's 22.4 liters for every 1 mole of gas. And you get a density of 0.09, and this is going to be in 3 significant figures, grams per liter. Okay, so look how light hydrogen is compared to chlorine. What about nitrogen? So in nitrogen, the molar mass of nitrogen is equal to 2 times 14.01 grams per mole. So I get 28.02 grams per mole for the nitrogen gas. The density that's a G, 1 mole for every 22.4 liters. And that's going to be equal to 1.25. So this is for nitrogen, and you can see the density is much greater than for hydrogen, which is why with the hydrogen generator lab, we had to store the bottles upside down, because as soon as you collected it, if the bottles were standing upright, it would just, it's so light, it would just float out of the bottle. And the nitrogen is so much more dense. Okay. What about reactions with gases? Oh my goodness. Well, there are 2 things. If everything's in volumes, then we can just use our stoichiometry and our volumes. But here's the other thing. If we have volumes in solids and all, then you're going to need to follow this solution map. Here, to go from grams to moles, which we did way back in chapter 9, you're going to use your molar mass. All right. If you want to get moles from given atoms or molecules, that was back in chapter 7 or so, then you're going to use Avogadro's number. If you're given the volume of gas, how do you get moles? You're going to need your pressure and your temperature, and then use your ideal gas law. And this is mirrored, same thing, if volume B here is a gas, then you're going to need your pressure and your temperature for the ideal gas law. Here, from moles of B to mass of B, you're going to need the molar mass of B. And then here you use Avogadro's number. But what about moles of A to moles of B? Notice it's still in moles, and all I'm doing is changing substance. So here you need a mole to mole ratio. So it's really important that you will add on to it a little longer, a little more in chapter 14. But it's really important that you know this construct, the solution map, really well, because you use it quite a bit. Okay? Now, at STP, remember how we use the molar volume here to go between moles and volume. So once you know what your pressure and temperature are, you can actually use a conversion factor if it's STP, if not, ideal gas law. Okay? So let's try practice. Okay, at STP. So we want the number of moles of phosphorus needed to react with 4 liters of hydrogen, okay, at 273 Kelvin and 1 atmosphere. So this is STP, isn't it? Okay, so why do we need to do that? Why can't we use volumes? Because look at phosphorus is a solid. So we're going to take our 4 liters of gas, okay, let me make that L look a little nicer, and we need to convert it to moles. Okay, so volume to moles, we're going to use our molar volume, right? So we know it's 22.4 liters for every 1 mole of hydrogen gas. But what we're actually after, we're after phosphorus, aren't we? So we're going to need a mole to mole ratio. So for every 6 moles of hydrogen gas, we get 1 mole of phosphorus to react. Okay, so now that I have moles of phosphorus, then we wanted just the moles of phosphorus. We don't need the mass. So let me erase this. So we can stop here and calculate it out. Okay, we have 4 divided by 22.4 divided by 6. I get 0.030 moles of phosphorus. Okay, so let me continue on. Okay, so let's do another practice. So here, I'm not at STP. But look at, everything's in the gas phase, right? So now, if everything is at the same temperature and pressure, then all I need to do is use my volumes, the stoichiometry, with volumes. We can do this because of Avogadro's law. Okay, so if I start off with 9 liters of hydrogen, and I want to know how much the volume of nitrogen, then we know with the stoichiometry that for every 3 hydrogens, I have volumes of hydrogen, have one volume of nitrogen. The hydrogens cancel out. I have liters, and 9 divided by 3 is 3.0 liters. So this is the volume of nitrogen that would react with it. Okay, what about this one? Now this one's a little different, right? So an air bag should be filled with a pressure of 1.9. Okay, so this is not STP. Okay, and you want to know how much solid. All right. So what are we going to do? You have the volume. Okay, we're looking at nitrogen because we're filling a gas, right? And Na is a solid. Now we want to go to moles of nitrogen. We want to go then to moles of my sodium nitride, and then to the mass. Okay, so let's go ahead and get our conversion factors. So we're going to do this in multiple steps. Okay, so the first part is going from volume here to moles of nitrogen. So we know, since it's a gas, PV is equal to nRT, and what we're looking for is N. So N, divide both sides by RT, PV over RT. Okay, so P is equal to 1.09 atmospheres. V is equal to 45.5 liters. Okay, T is 22 degrees Celsius. So we add 273 to this, and we get 295 Kelvin, and we know R. So let's go ahead and for step 1, calculate N first. We're going to do just this one. Okay, so N is going to be equal to 1.09 atmospheres times the 45.5 liters divided by 0.08206 liter atmospheres per mole Kelvin, and T is 295 Kelvin. Okay, so if we cancel out our units, that looks good. Liters cancel out, Kelvin, so we're going to get moles for our units. That's good. That's what we want. Okay, and it should be 3 significant figures. So 1.09 times 45.5 divided by 0.08206 divided by 295, and we get something like a 2.0487. We want 3 sig figs moles of nitrogen. Okay, so let me go ahead and put that right here. So N is equal to 2.0487. We want 3 sig figs moles of nitrogen. Okay, and the reason I'm doing that is my limited space. Now what we're going to do is we're going to do the rest of these. Okay, so let's go ahead and do the rest now that we've determined what N is. Okay, so and a solution map doesn't necessarily mean that everything has to be done in one large multiplication t squared. Okay, all it means is that we're defining the number of steps. So we did the first step. So now that we have the number of moles of nitrogen, we need our mole to mole ratio, which we're going to base it off of our coefficients here on the balanced equation. And we need the molar mass of sodium nitrite. So let's get that first. And then we'll do our calculations. So the mass of sodium nitrite looks like this. So the molar mass of sodium nitrite, it's 22.98 plus 3 times 14.01. The units are going to be in grams per mole. So we have the 22.98 for the sodium, or 99. 3 times 14.01, because I have 3 nitrogens. And I get something like 65.01 grams per mole. So now we can go ahead and finish our steps. So instead of starting here with the volume, I did this part separately with my gas. I'm going to start here now. So 2.0487 moles of nitrogen, that's going to be in 3 figures, times, we know it's going to be, we want the sodium nitrite, so 2 moles of my sodium nitrite for every 3 moles of nitrogen gas times my molar mass, and that should be 65.01 grams of sodium nitrite for every mole of sodium nitrite. So let's check our units. Moles of nitrogen, that will cancel out. Moles of sodium nitrite cancel out. So I'm left with grams of sodium nitrite, which is our desired unit. Okay, so 2.0487 times 2 divided by 3 times my 65.01, and I get something like 88.8 grams, okay, of sodium nitrite. All right, and that's how much we need to fill the bag. So we know solid sodium nitrite, and we got the mass for it. All right. We'll use our stoichiometry, and we got the 88.8. So this is, again, like we've been doing with chapter 9, all we're doing is expanding on that solution map and including gases as part of it. Okay, so let's do one more. So we want the volume of oxygen at 760 torr and 25 degrees Celsius. Okay, and we need a fully reactant with 3.2 grams of ethane. Okay, so in this case, we're starting off with the mass of C2H6. We need now to go to the moles of ethane. Okay, but we're interested not in that, we're interested in the oxygen. So we need the moles of oxygen. And then we wanted the volume. Okay, and while this is equal to the same as 1 atmosphere, this is not STP, because this is, if I add my 273, this is 298 Kelvin. So we're not at STP. So when we get to this last step, we're going to get the moles of oxygen, and then we're going to do a separate step. Step 2, we'll do this last one. So what we're going to do is get our conversion factors, go from here to moles of oxygen, and then we'll use our ideal gas law to do the last step. So the molar mass of ethane is 2 times my 12.01 plus 6 times my 1.6 times my 1.008 for the hydrogen. All of this will have units of grams per mole. So the molar mass is equal to 30.07 grams per mole. Okay, so we have this conversion factor. Okay, the next conversion factor is our mole to mole. So the mole to mole, we know for every 2 moles of ethane, I need 7 moles of oxygen. Okay, so let's go through and get to moles of oxygen. So we have 3.2 grams of ethane. Okay, and we're going to react that with, not react, excuse me, we're going to get the moles. So 1 mole of ethane divided by the 30.07 grams. That's a 6. That'll convert this into moles, and then my mole to mole ratio, which we said 7 moles of oxygen for every 2 moles of ethane. And that's going to be equal to 3.2 divided by 30.07 times 7 divided by 2. And we get something like 0.37246 moles of O2. And we know we want 2 significant figures. So I'm going to write above N is equal to 0.37246 moles of O2. My 2 significant figures there. And now let's just give me space to use my ideal gas law. Okay, so we finished the first 2 steps, and now we have to do the last step. And so the last step right here, I'm going to give the check mark. Okay, here we need our pressure and temperature, and we're going to actually use our ideal gas law. So with our ideal gas law, we know PV equals nRT. In this case, we're looking for volume of oxygen, so the volume is equal to nRT over P. So let's put in our values. We know N, R, T we said was 298 Kelvin, and P at 760 torr is 1 atmosphere, and this is going to be 36 figs. Okay, so volume is equal to 0.37246 moles of O2. Remember, that's going to be 2 significant figures, times R, 0.08206 liter atmospheres. Let me just move this over a little, give myself a little more space. Okay. Okay, so V is equal to 0.37246 moles of oxygen. R is 0.08206 liter atmospheres per mole Kelvin. And T was 298 Kelvin. Okay. We know this is 2 significant figures. Okay. Pressure was 1.00 atmospheres. So let's check our units, make sure they cancel out. Atmospheres, that cancels out. The moles cancel out. Kelvin cancels out. So my units for a volume will be in liters. So that's good. Okay, so let's multiply this out. 0.37246 times 0.08206 times 298. Okay. And then we want two significant figures. This is 9.1 liters is the volume of oxygen that you'll need to react with 3.2 grams of ethane. Okay, let's try one more practice here. And this practice, we want the volume of hydrogen, okay, at 739 torr and 21 degrees Celsius. And we want to know if it's liberated by 42.7 grams of zinc. So we're starting off with the mass of zinc. We need to go to the moles of zinc. Then we need to go to the moles of hydrogen, right? And from hydrogen, we would need to do the volume of hydrogen. Now, since this is not an STP, we're going to use the ideal gas law. So like we did in the previous slide, we're going to do the first two steps here, and then in a separate step for the ideal gas law, we'll get the volume. So what do we need as our conversion factors? We need the molar mass. So the molar mass of zinc, just look it up, and we get something like 65.38. And if we look at our mole-to-mole ratio on our balanced equation here, we find that the mole-to-mole is 1:1. Okay, so let's go ahead and put this together. So we started off with 42.7 grams of zinc. We're going to convert that to moles, so we're going to divide that by 65.38 grams for 1 mole of zinc. And we know that it's a 1:1, so 1 mole of zinc will give me 1 mole of hydrogen gas. When we do this, we get 42.7 divided by 65.38, get 0.6531 moles of hydrogen. Okay, and I need a zinc here. Okay, so mass of zinc divided by grams, moles of zinc, and it's 1:1. Moles of zinc cancel out. Okay, perfect. So now let me put N up here. And this is going to be, when we're done, this should be in 3 significant figures, right? Okay. So now we need to collect everything we need to do this last step. Okay. So let's do this last step now. And that's going to use the ideal gas law. Okay. So let's write that down. All right, so for the ideal gas law, we know that PV is nRT. We want the volume, so the volume is equal to nRT divided by P. So I have N, we know R. Pressure is in torr, so we need to convert that. And we know that 1 atmosphere is the same as 760 torr. Again, make sure you have your conversion factors in front of you. So that gives us a 0.97237 atmospheres, and we will want 3 significant figures on that. Our temperature is equal to 21 degrees Celsius. We're going to have to add our 273 to that to get it into Kelvin. and that's 294 Kelvin. So now that we have all our values, what we're going to do now is just plug the numbers in and calculate out our volume. So volume is equal to 0.6531 moles of hydrogen gas times R, 0.08206 liter atmospheres per mole Kelvin, times our temperature, which is 294 Kelvin. Okay, and all of this is divided by our pressure, which we determined was 0.97237, but we want 3 significant figures, atmospheres. Okay, so will our units cancel out? Moles cancel out, atmospheres cancels out, Kelvin cancels out. So our units will be in liters. So that's good. So let's go ahead and do our numbers. So it's the 294 from the temperature times our 0.08206, okay, times N, which we had determined from our previous calculations, so 0.6531, okay, and divided by our pressure, which we did our conversion, 0.97237, and so we get something like 16.2 liters of oxygen, which is right here. Okay, so that's going to be the end of our gas chapter, and make sure you do your breakout session number 11.